So we've learned that the correlation coefficient can gauge strength and direction of our linear relationships, but we kind of breezed by something that we need to look at again, which is that we're never going to find this by hand. Instead, we're going to use the calculator to find our value for us when we're given a data set. Obviously, if we're not given a data set, if we're just asked to kind of gauge it from a matching problem, then that's something different, like we just did on the last example. But if we want to find it with our calculator, we're going to need to be able to do an example like that. All right, so the following table lists the percent of students who receive free or reduced price lunches compared with the percent who pass the math portion of the state exam at public schools in Sandusky, Ohio. So it's sort of like most states have some kind of test that students have to take in high school to kind of prove efficacy of education in that school district and so on. So and a math test is one of those tests that students have to take. In Michigan, we take it in like the 10th grade and the 7th grades. We call them the MEP tests, but in Ohio, they're called something else. But suffice to say, each of these lines represents a high school. So there's a high school here that had 29% of its students on free reduced lunch. 66% of those students passed the math test. And then another school with 29% of the students on free reduced lunch and 59% passed the math test. Notice the number 29 goes to two different values. That's because this is not algebra class. This is statistics class, so things are a lot more squishier for us than they are for an algebra class. Okay, so what was the sample size? Well, to get that, we would just have to count how many rows there are here in this table, because these are all the different schools. So there's, by my count, 13 different rows. So our sample size is 13. So they were 13 public, it says public schools, but I believe they were high schools because of the way this particular problem worked. But I guess I'll just say public. Maybe they were middle schools too. All right, what is the explanatory variable and the response variable? Well, the explanatory variable is the one that we are trying to see whether it has an effect on the response variable. The response variable, in other words, we're trying to see if that one responds to something. So you can imagine that what they want to do is say, hey, what makes it so that some students pass the math test and some students don't? And why is it some schools have higher rates than lower rates? So the percent passing the state math exam is the response variable. Now, that's something that politicians and so on want to look at. They want to see what it responds to, right? They would like this number to be higher or lower. So what they'll do is they'll go look at different explanatory variables. What are some reasons why some states or some schools are higher than others? What are some things that could explain that? So the explanatory variable, which is your X, is the percent of students on free reduced lunch. And there we have it. So it's a little strange, but basically the response variable is the thing that they're trying to figure out. Like, why is it that this is higher sometimes and lower other times? And explanatory variables are variables that might affect that response variable. What are some things we can do, some things we can change, things we can manipulate, and see how it affects the response variable? In a weird way, the response variable is usually the variable of interest, the thing that's really important. And then the X variable are one of many different things that we could use to manipulate it. Keep in mind for state math exams, there might be a lot of reasons why some schools are higher than others. Maybe they have more money devoted to math programs. Maybe they have, I don't know, robotics team. Maybe they have, et cetera, et cetera. All right, we need to calculate this correlation coefficient with our calculator. So we are going to go to our calculators. So let me go to, now first things first, this is a one-time only deal. You won't have to do this again once we do it this one time, but you're going to turn the R feature on, if you will. You do that by going to Mode and going down to the bottom where it says Stat Diagnostics. Down here. You might have to arrow down to it. If you're on an older calculator, it might not be on this screen, but kind of scroll down to Stat Diagnostics and press Enter on the on. So I arrowed over to the on and I pressed enter so it's dark. So when I move off of it, it's dark. That's all you have to do. On older calculators, what you'll have to do is go to the catalog and you have to scroll down to the D values. So you hit the X to the -1 button, it'll take you to the D's, and you have to scroll down. You're looking for diagnostic on. and there it is. And you hit enter and hit enter, done. So one of those two methods. So go to your mode screen. If it's in the mode screen, then great. If it's not in the mode screen, then go to the catalog and get it there. And again, this is a one-time only deal. Basically, by doing this, you have turned R on. And now it will be on forevermore until you turn it off. Simple as that. Okay, so now I need to go to Stat, Edit. If you have any old data, clear it out, and you're going to type in the new data. So 29, 29, 23. You put your X's in L1 and your Y's in L2. So let me type this up 1 second. There, I have all my data points in, and I wrote here just real quickly so everybody sees. The explanatory becomes your L1, the response becomes your L2. Okay, so make sure you do it that way. And then when you go to Stat, again, you're going to press Stat and calculate, but instead of doing number 1, which is what we did in chapter 3, we're actually going to move down to number 4, which is linear regression. So we're pick number 4, linear regression. We want to tell it that the X list is in L1. That's where our explanatory variable is. So you hit second one if it's not already there. It is in our case. And L2, we do not use frequency lists. The only time we ever use frequency list is in section 3.3 or 6.1. That's it. The rest of the time, we just don't use it. Now, storing the regression equation is a choice. You can do it or not do it. We're not actually using the regression equation for this section, but we will in the next section. So I'll teach you how to store it if you want to. So you press Variables, move to the right to Y variables, pick number 1, and choose number 1. That's an optional thing. You don't have to do that part if you don't want to. But the L1 and L2 at the top, you absolutely have to do. Then you go down to Calculate and press Enter. And it'll run it, and you can see that the R value is right there. It's negative 0.688. So there's our R value. And that's how you calculate it. Easy peasy. Okay, now what kind of relationship does there appear to be between the percent of children on free reduced lunch and their math scores? Well, that's a negative relationship, and at 0.688, that's a moderate relationship. Let me scroll back to the table so we can double check. Okay, negative 0.688 falls in between negative 0.5 and negative 0.8. It's in this zone, this blue zone over here. So it is a moderate negative relationship. That means that if X goes up, Y goes down. That's what a moderate negative relationship would be. So if a school has a higher percentage of students on free or reduced lunch, then we can expect that they'd have a lower percent of students that would pass the state math exam. So as X goes up, the percent of students on free reduced lunch, then the Y goes down, right? We expect that school would have a lower percentage of students passing the state math exam. Now, it's not a perfect relationship, obviously. This is a moderate relationship. So, I mean, that's one of the reasons I've used the word expect. You know, we expect it to go down, but we don't say by how much. We're not really sure yet. We'll get into exactly how much later in section 4.2, but this is the trend that we're seeing. And so all I'm doing here is describing that trend in words. So the X bit is the first phrase, and the Y bit is the second phrase. All right, now why would this study have to be observational? It actually can't be an experiment, not ethically. And that's because to be an experiment, you have to randomly apply the treatment, right? You have to randomly apply the X, which would be free reduced lunch. Well, you can't do that. You can't say, hey, student, no matter what, you're going to get free reduced lunch. And they'd be like, I don't need it, but it doesn't matter, you're getting it. And you, student that can't afford lunch, I'm not going to give it to you. Right? I just randomly chose you to not get it. That's not fair. That's not ethical. Can't do that, right? It would have to be observational. You'd have to be observing the kids that are already getting free reduced lunch and not getting free reduced lunch. You can't force it upon them. That's what it would take to be an experiment. All right, so I just typed that up. An experiment would mean the researchers randomly assigned free reduced lunch. That would be unethical. That is bad in research. So instead, researchers would just observe the passing and free reduced lunch percentage that already exist in those schools. They're not going to force kids that are hungry to go hungry, and they're not going to give lunch away to kids that don't necessarily need it because they already have it, right? That would be terrible. All right, now why is it not possible to argue? And I've been trying to be very careful with my language. We don't say that free reduced lunch causes the lower exam scores. I don't say that, yes, it's a moderate negative. So I don't say, hey, if we have a higher free reduced lunch, then automatically you're going to have a lower percent. What I'm saying is that if a school had that higher percentage, we kind of expect it to be lower, but it doesn't mean it's lockstep causation. Well, why not? There's a lot of reasons, but one of the overarching reason is basically a lurking variable. There are other things that go on with why some students pass math exams and some students don't, and why some schools are higher and lower, and the free reduced lunch alone doesn't really get at all of that. So let me type that up. All right, so you've probably heard this in science class or another math class somewhere, but we'll say it again. So having a moderate negative relationship, having a moderate negative correlation, which is what we do have, but it's true for any correlation, does not mean causation, right? You wouldn't mean it even if it was strong, right? So correlation does not mean causation. And that's because there are things called lurking variables, which you hopefully learned about in section 1.2. They're variables that have an effect on both have an effect on both the x and y variables. In our case, x was free reduced lunch, the free reduced lunch percentage in the school, and the y, which was the passing math percentage in the school. So we would want to look for potential lurking variables that would fit this situation. And what you're looking for is something that really affects both of these things, not just one or the other, but both. Right? That's where the real good stuff is. So something that would affect whether a school has a high free reduced lunch percent and a low math percent, or vice versa, a low free reduced lunch percent and a high math percent, which the income level of a school or a school district, of the people that live in that school district would be a big one, right? Because poorer schools tend to have high free reduced lunch percentage, tend to have low passing math. So income level, poverty level. What's the poverty level of your school district? What's the income level of your school district? Those are kind of two ways of saying the same thing, right? So both of those would have an effect on both of these variables. I think, what's the culture? How much does your school district value these things? The culture of the school district. So you might be in a school district that for whatever reason really doesn't value education, or doesn't value, I'm just trying to think, free reduced lunch, but truly doesn't value looking after kids for whatever reason. So perhaps that's something that's going on. What's the parental involvement? It takes parental involvement to get kids on free reduced lunch. So the parental involvement in that school district might have an effect. And I could keep going on and on and on. This is what people spend their lifetimes studying in graduate school for education, but you get the gist. So when you're writing up a question like this, you want to have three parts to it. You want to talk about how correlation is not causation, right? That's the first bit, right? In this particular instance, it was a moderate relationship, but it could be strong, it could be weak, it could be whatever, right? But the correlation, well, not weak, but strong or moderate, does not mean that you have causation. That's the first bit. And the causation right here was the key to this. So I knew once I saw causes that this is what we were talking about. But that alone won't get me all the points. Then I have to describe why it's not happening. So I have to talk about the lurking variables, right? And then I have to give some examples. What's something that suits this situation? And there could be lots of them. There could just be one of them. There could be a couple of them. But you're looking at something that affects both the X and the Y. That's key. So look for something that's going to have a relationship with both of them. And I came up with a whole bunch in this particular example. So those would all be potential lurking variables. You don't have to write all of them. Write a couple of them. I mean, for your notes, write all of them. But when you're on a question for your your exam or for your paper pencil packets or for your worksheets. Just write one good one. That's all you really need.